Thank you very much for the introduction and for the invitation. It's again an honor to be back here. I was last year, about the same time, talking about a very different topic. Today I'm going to talk about imaginary light, or situations in which there is no light at all, or it's simply non-existent changes in the light information and so on. But before I get to imaginary light, I'd like to talk a little bit about real light, physical light. Okay? So when light hits the eye, there is a reaction which is known as a pupillary light reflex, which happens automatically. We cannot control it, we cannot stop it, and very fast. It's there for a lot of different reasons. To protect the eye, the photoreceptors in the retina from bleaching, from excessive light, and also to focus, to adapt to the light conditions to achieve the optimal depth in vision and so on. It is often described as a kind of servo mechanism, if you want to use a term in engineering, in bioengineering as well. It's like a closed loop type of servo mechanism. The biological equivalent of the photocell controlling a door opening and closing, for example, when you enter a shop or the bank and so on, automatically closing. And it doesn't matter who's going through the door, as long as there is a body there that is moving and is stimulating, the door will close or open. Okay? And it seems that it's the same here. It doesn't matter what kind of information light is sending to the brain. All that seems to matter is how much energy in physical light is stimulating the eye. And it could be anything out there. So my talk is actually about a correction of this type of standard view on pupillary control, showing that the content of information of light plays a role in how the pupil actually adjusts itself. Okay? So to summarize, the pupillary light reflex is considered a biologically closed-loop servo mechanism that is controlled by this subcortical network that reacts to changes in light, independent of higher parts of the visual system interpret light. I think this part is wrong, okay? And the reason it's wrong, it's already present in the neurophysiology. Now we know much more about the circuitry, the neural circuitry that controls the pupil. So this part, which is the subcortical root, that controls the pupillary light reflex, it has been known for a long time. So when light stimulates the retina, okay, then there is a series of activation of neurons, not that many synapses, 1, 2, 3, 4, and then the pupil reacts. So that's one of the reasons also that it's so quick, and it is important that it acts so quick. But as you can see in this neural circuitry, which has been updated in recent years, as a matter of fact, this is from 2008, there is a whole part of the circuitry which goes beyond this simple mechanism and includes other parts in the subcortical structure, like the locus coeruleus. This is the hub of the noradrenaline system, and therefore it's linked to a lot of cognitive and emotional type of reactions and so on, which can modulate the activity of nuclei at different levels that control either the dilation or also the constriction of the pupil. Plus, the locus coeruleus is in dialogue, interaction with a lot of cortical structures, some of which are also very important for cognitive processes and emotional processes. So there is a whole part here which is relevant. I'm not going to show you any neurophysiological results today. I'm going to focus on some results from my own laboratory, which is actually psychophysiology, not neurophysiology. And what we have been doing is to show to participants who are students at the university objects like this. Now we are in Japan, therefore I believe most of you have probably seen these kind of graphics because it's been designed by Akiyoshi Kitaoka at Kyoto University. I borrowed his stimuli and he called this one Asahi for obvious reasons and so on. So what's peculiar about these objects is that probably independent from where you are sitting and how far or how close you are from it, it looks like that there is in the middle, in the center of this image, there is a light, a bright light, okay? Like a source of light. But the truth is that the white that you see here and the white that is all around in the background is exactly the same, okay? So if we cover this stimuli, you can see that this and that is exactly the same white. And it's a classic illusion effect because now even after knowing that this and this are the same type of white, you still see this whiter than white. So it falls into the classical class of optical illusions. So we use this kind of stimuli. In fact, I borrowed Asaki from Kitaoka and turned it inside out. So this is my version of it. Again, this is a very good control stimulus for the original stimulus because it has exactly the same elements. You can count them. Therefore, the average luminance of these objects and the average luminance of these objects is exactly the same. However, you probably agree with me, this looks much brighter than this one. In fact, this looks a bit darker than the background type of illumination. In a way, we have reversed the illusion. But again, physically, out there in the world, nothing has changed. What is changing is something within our own head, in our brain, that makes us forcefully, automatically, without our will, to interpret this as a source of light and this as a darkness. But they are the same. There is also another class of called lightness illusion because now the effect of luminance seems to be reflected from the surface instead of being generated by a source of light, as in the previous class. This is the famous Canizza triangle. Canizza was a psychologist from Italy, so a national of mine. When these elements, the Pac-Man, are in the correct orientation, we have a strong sense that there is a form there that is actually not there, a triangle, because we can even perceive contours, lines that are not there, and neurons, in fact, respond to these locations as if there was a line. But what I think is most remarkable about this Canizza illusion is also the fact that this surface, illusory surface, looks whiter, looks brighter than the background. And the more you believe there is a triangle there, the greater is the effect of light. So that this triangle here should look a bit brighter than this here, and this here, and that there. Do you agree? This is purely phenomenological, okay? Because again, the white here, the white there, the white there is always the same. So what we do in our lab, we have a technology which has been developed enormously in the last few years. It's based on infrared video camera. So that participants can sit in front of a computer. Here there is a video camera that has an infrared lamp. And we can monitor what happens to the eye while they're looking at something on the computer screen. All of these systems were originally developed as eye trackers to track the movement of the eye, but because they're all in common that they track the position of the pupil, of the eye pupil, then they also collect information about the size of the pupil. The sampling rate can be extremely high, and therefore the information about changes in pupil diameter is available from these eye trackers. And that's what we are actually interested in. Because what we wanted to do is to see when we present the stimuli for just a few seconds, and the task is the simplest I've ever used in my career, because it's simply looking at what's on the screen. There is no response, there is no further instruction, there is no question asked to the participant. It's simply look at what's on the screen, because what we are interested is in the response of the pupil spontaneously, okay, without any other type of influence on the participant. And when we look at the responses of the pupil, so just to explain, all the graphs work in the same way. We have at the beginning a baseline, which is a neutral screen, which is isoluminant of the same luminance of all the stimuli that are presented. So we subtract the pupil diameter in that baseline from the pupil diameter in response to each stimulus. When you do that, what you get is the pupillary response, not to light per se, not to physical light per se, but to the cognitive response to the stimulus. So that everything below zero, so below baseline level, is a constriction of the pupil, and everything positive above zero is a dilation of the pupil. As you can see, all stimuli constricts the pupil. That is to be expected whenever you change from a blank screen to something which has spatial frequency. So that's a classical response to a pattern type of information, so that the pupil adapts very quickly. But what is most important is that the subjectively brighter stimulus provokes a greater constriction, which remains for the whole time of recording, which is 4 seconds. And it's the same with the lightness illusion, this Kapitsa illusion. So the brightest will constrict more the pupil, then the less bright, and so on, in a very systematic relationship. Okay? So this is published in 2012. So on average, the pupil constricts more to stimuli that subjectively looks brighter than stimuli that are exactly the same in luminance, but subjectively look less luminant. In fact, what you see here is the psychophysical measurement in which we present the stimuli side by side and ask participants in a separate session to tell us which one looks brighter. Choose between the two. So that this is the phenomenology and this is the physiology. As you can see, they match each other. So they are mirror images of one another. When this is objectively high, then the pupil reacts more. And so on. And that this happens also for these class of stimuli. Okay? Although the brightness illusion is more powerful than the lightness illusion in provoking this response in the pupil diameter. So to summarize, what we can conclude is that the pupils reflect what we think we see. And the pupillary responses reflect the perceived brightness or lightness of the seen objects, and not just the amount of physical light energy entering the eye. So it's not a closed-loop servo mechanism and so on, which is ignorant or uninterested about the content of the information. Such a pupillary response to illusory light is likely the outcome of top-down signals from higher level areas, subcortical areas controlling the pupil. Based on the neurophysiology that we have on monkeys, based on fMRI studies that we have on humans, independent, we know that there are neural structures and networks that most likely are behind this effect, that are already at the cortical level. So this means that the response is very likely to be an interactive feedback between cortical areas that interpret the information and those subcortical structures that control the pupillary reaction. A year later, a group at University of Washington in Seattle published another pupillometry study where they show these pictures. Again, A, B, C, and D, they're all the same luminance. They've been matched by luminance. So this is just a neutral field, this is scramble field. Then there is a photograph of the moon and a photograph of the sun. Okay? What's interesting about the photograph of the sun is that it shows this glare effect. And this glare effect, this idea that we interpret this as a source of light, is capable also to constrict the pupil a little bit compared to all of the other pictures. So there is something about this pattern of light diffusion that is important, that the eye and the brain interprets as a clue of some kind of stimulus that needs to be responded to. So if we put this together, it's likely that what we are observing is a response to things that happen in nature all the time, like this one. So the existence of glare, the existence of the possibility of being dazzled by light, okay? Which of course is not a good thing. It can be a rather dangerous situation. I'll come back to that to the end. What I want to do now is to describe another property that has been described rather recently about illusion. So this is a different kind of illusion. It has nothing to do with brightness or lightness and so on. It has to do with size. So it works on most people, not everyone. And this is the Ebbinghaus illusion. This circle here, okay, looks of different size than this circle here. In fact, this should look a bit smaller than this one. Do you agree? Yeah? But again, the truth is that they are exactly the same size. Now, based on several schools of psychology, eminently James Gibson and so on, who have claimed that optical illusion work the way they work because they present very poor type of information. Information is lacking, and if we add information, then the illusion tends to disappear. Well, it turns out that at least in some cases, perhaps in most cases, we don't know yet, if you add information, very often the illusion actually gets stronger. So, for example, if we add movement to this particular illusion, the illusion gets much stronger. So, as you can see here in the animation, if you focus on the center circle, everyone should have a very strong sense of the circle changing size, becoming smaller when it goes down or larger when it goes up, okay? But if we actually split the animation so that we can see what actually constitutes these images, okay? Then you can see, you can clearly see that the central circle is always the same size. Okay? It's only the outer circles that are changing. The effect is very strong. Okay? So the question is, can we generalize this enhancement, this boosting effect of illusion also when it comes to this brightness illusion? So that's research that we are conducting right now in Oslo in collaboration with Zavagno, an Italian perceptual psychologist, an expert in this kind of stimuli, and another colleague in Italy. So we show glare patterns. So you would agree with me that this shows the same type of effect that we saw originally with Asahi of Akiyoshi Hitoka. There is a sense that there is light here, which is diffusing out from the center of the stimuli. If we rotate a bit these elements, as I did here, the glare effect now it's not corresponding to the same central location, so it's greatly reduced, it's weakened. And this is an isoluminant stimuli to all of these three stimuli, so which has no glare whatsoever. That is our baseline, in a sense. Okay? So we're showing these elements. We also show a reversal of the illusion, where we just reverse black and white And surprisingly enough, we get the same effect this time in darkness. This is puzzling because we don't experience in nature black light. There is no such thing like black light. Darkness is an absence of light. Although physicists talk about dark forces, that is invisible. But so this is probably most likely described more appropriately as a smoke illusion or a fog that is diffusing out of the center of this image. But what is important for us is not so much what is creating this illusion, but how the eye pupil will react to it. If our hypothesis is correct, hypothesis that the pupil adjusts to what we think we see, then in this particular situation, the pupil should dilate, should not constrict. Okay? It's only when it's bright white that should constrict and so on. So we are testing these things. Again, with the same paradigm, we show these objects for a few seconds. Participants just have to fixate in the center of the cross, and that's it. Very, very simple. And we measure at the same time the pupillary response. But we have also another type of stimuli, which is animation of the glare effect. So at the beginning, all the square starts like squares, and then the ramps, the gradients, change slowly, so that this glare increases over time. But what is most important, it reaches the same level of glare that we have in the static stimuli, and will stay on screen for the same amount of time that we show the static stimuli. So what we want to know is how the pupil will be when looking at exactly the same object out there in the world, but having been preceded by information showing a gradual development, a motion towards the identical state. So, we have also then for the darkness, these are superimposed eye movements of four participants and so on. So again, we're interested in what happens, in what state is the pupil when this stops, essentially, when the animation stops, to compare it to the static version. So when we look at the results, we find that, again, that the white glare stimulus constricts the pupils. It does that more than the control stimuli. But we also find that the black glare stimuli now dilates the pupil, and it does it more than its control stimulus. But when we look at the dynamic stimuli, now we see that the effect of both the black and the white glare is amplified. It's become about the double of the original effect, which is a bit consistent with what the researchers that investigated the Ebbinghaus illusion reported, that the Ebbinghaus illusion was rated subjectively as double strength than the original illusion. So it generalizes very well to this situation. Okay, for the second part of my presentation, now I'm going to talk about imaginary light per se. The idea for this series of experiments derived from my reading of a book published in 1883. If I read correctly the poster for this conference, Wilhelm Wundt established his first psychology laboratory in 1887, right? So this is a few years before Wundt established his laboratory. And it's a book by Sir Francis Galton, so this is one of the forefathers of psychology. It's a very interesting book. The reason I read it is because there were two chapters in the book. One about synesthesia, which is an interest of mine, and another about mental imagery, which he calls mental vision, and so on. Galton was a very interesting man. He was a member of the British Royal Society of Science. He was a cousin of Charles Darwin. So he was also very much influenced and interested in the idea of heredity and so on. But in this chapter, where he discusses mental imagery, he raises a series of questions that he would like to get an answer. And reading the chapter is amazing because a lot of the questions that we process are the questions that drove, much later, the whole program of mental imagery research. Ulrich Neisser, Donald Hebb, my mentor at Harvard, Stephen Koslin, are repeating very much the same questions that Galton posed already. There is one question in particular that attracted my interest, and it's the following question. So this is a direct quote of Galton, sorry, this one. If you can go back to this one. Is the brightness of a mental image comparable to that of the actual scene? Why is he posing this question? Because Galton had the idea that also have, or contemporaries like us would have, that imagery is like perception, and therefore it should have many of the aspects of perception itself. The same sensible features that we have in perception should be present in imagery. So, of course, this is 1800s. He didn't have the methods that we have today. In fact, he had to invent a method, and the method that he used was the same method that Wundt used at the same time. It was introspection. It was simply to ask people what they thought about this particular issue, and so on. And since he was a member of the British Royal Society, he invented a new technique which is called questionnaire. I believe he was the first person ever to use a questionnaire, to compose a series of questions that he would distribute to people, and they would have to write their answer to each one of these questions. And his subjects were the members of the British Royal Society. In fact, all of them filled Galton's questionnaire about imagery and gave it back to him, 100% participation. So the greatest minds in Britain at the time were the subjects in this experiment. And what's interesting is that he thought of posing very specific questions so that people could actually focus their attention on this issue. So one of the questions was what has become now well known as the breakfast table questionnaire, is think of some definite object. Suppose it is your breakfast table as you sat down to it this morning. So he's thinking about an experience that everyone does every day so that they can relate to. In fact, what you had for breakfast this morning and how your table looked like and so on. And consider carefully the picture that arises before your mind's eye. So this is Britain, Victorian age. So probably people would think something like this, okay? Nice egg and bacon, a cup of tea, and so on. And people answer this questionnaire, and of course, there was a great variation in the responses and so on, but there was a great majority of people who claimed that they could do that. So what we decided to do about 103 years later in Oslo is to test Francis Galton introspection with the help of today's eye tracking technology. Now we can answer precisely Galton's question by measuring the response of the people, why people are considering the same kind of situations that Galton was thinking about. So if you, yes. So we decided to start rather simple, according to the classic paradigm of experimental psychology. So we show triangles. So we have a baseline, then a triangular stimuli, which stays for a few seconds. This is the perception phase. Then we have a dark stimulus. The reason is that we don't want the pupil to slowly return to baseline. We want the pupil to return to baseline quickly. And therefore, we show a black screen. We adjusted this, and then there is the key part, the imagery, which is just as long as perception, but this time there is nothing on screen. It's completely blank. Okay, but people keep their eyes open, and now they have to do one task. The task is to imagine that on the screen is the same object that they just saw, which is this triangle. What is happening during the experiment, this is just 2 trials, is that the triangle is sometimes up, sometimes down. That is relevant. What is relevant is that the triangles can vary in brightness. So this is dark, this is light. We have different levels of luminance of each of the triangles. Okay? So when they're looking at triangle, this is from the eye tracking. You see people look carefully at the shape. They know they have to remember it and so on. And this is also typical of eye luminance. All these circles have fixations and so on. And so people focus on the contours. Of course, those are the regions in which the luminance between figure and background are most different. They also like the corners a lot. Corners are important in defining shape. And they also look at the center, because in the center is the color and reflectance information of the surface of the shape. If we look at this shape now with superimposed the group focus of attention, which is where they were looking, so this is overt attention, we see that very clearly. Corners, center, and along the contours. Okay? So this is during a perceptual triangle, where they're looking at this particular triangle. This is another triangle. Okay? Darker, upside down, you see the eyes follow nicely the shape. What's important is what happens when they're just thinking about this object, and there is nothing on the screen. The screen is empty. Something like this. As you can already get a bit of the sense, there is a triangular shape here that is being formed by where the eye is focusing. In fact, if we plot by taking the XY coordinates of the screen, all the fixations of all subjects in all trials, for triangles going up, this is blue, and triangles going down, which is in red, is hundreds of thousands of fixations, because the sampling rate is very high in the eye tracker machine, and these are lots of trials and presentations of several seconds. So these are a lot of data, but you can see clearly that people, in a way, draw with their eyes what they are seeing, during perception. That's kind of obvious during perception. But during imagery, this is less obvious. As you can see now, red is looking down, blue is looking up. There is absolutely nothing on the screen. This is just the coordinates of the eye while they're thinking, imagining seeing these objects. In fact, we could take this group performance and guess with high accuracy what those people were thinking about in a particular time. Whether they were thinking about a triangle going up or a triangle going down. So we can use this instrument for mind reading as well, reconstructing what the person is thinking just by looking at his eye movements. This was not Dalton's question, though. This was Donald Hebb's question that I've been investigating for years. In fact, my first work focused on the pattern of eye movements. But we want actually now to get to Dalton's question. So we're interested in the pupillary response when the luminance of the triangle that is being seen is blue, or it's being imagined is in green, is how does it change for all of these different levels of lightness, of gray, of the triangle. And as you can see, as the triangles get lighter, the pupil, this is pupil size, constricts. Okay? That should be that way in perception. This is absolutely normal. What instead should be surprising is that the green line, this is when there is nothing on the screen, is also highly correlated, and it also constricts with the imagining triangles that become progressively luminant. So this is the key finding. One could raise an objection that has been raised historically to the whole study of mental imagery. Because nearly every study of mental imagery, with the exception of some neuroimaging studies and so on, simply measures behavioral data which could be contaminated by people complying to the task demands that the experimenters have. So we can guess what the experimenter wants, and consciously or unconsciously change our behavior so that it will fit with the hypothesis of the experimenter. So Stephen Koslin, for example, received systematically this kind, or Steven Pinker as well, many of the contemporary, this kind of criticism in their research. In my opinion, this possibility is non-existent in this particular case. Why? Because differently from most behavior, we cannot control voluntarily the size of the pupil. So even if we wanted to do, even assuming that we can guess what is the hypothesis of the participant, of the experimenter, sorry, even if we wanted, we cannot do that. So this is in the pupillometry literature, which comes from studies in medicine, it comes from studies in physiology, it's been known for more than 100 years. But we decided to test it, nonetheless, with our own participants, just to show that the participants who gave us those results, they couldn't have possibly made those results voluntarily, that it was a spontaneous reaction during the task itself. So we asked our participant in an additional task at the end to dilate or constrict the pupil at will. We said, please, now you dilate your pupil. Now you constrict your pupil. And we measure the change of the pupil. We have two conditions. One, with a blank screen, which is exactly as it was in the experiment. And one when we even try to help the participant to actually succeed in doing it. There is a remote possibility that if you see a shape like that, these are the shapes that we actually use in the experiment, and you know quite a lot about pupillary dilations and the effect that changing the size of the pupil has on vision, then you could, if you are a very smart participant, think that if I'm asked to dilate my pupil, then the luminance of what I'm looking at should become higher, because there is more light entering the eye. So if I dilate my pupil while looking at this triangle, the triangle should look brighter and brighter over time. If I'm doing the opposite, if I'm constricting the pupil, then this triangle should look darker. Are you with me? Okay? So we have a condition in which this perhaps could happen. The truth is that when we actually measure it, there are two conditions. With the blank screen, with the form, they do not differ from one another. This is non-significant. In fact, there is even looking at the graphs a sense that if something is happening, it's not happening in the predicted direction. So there is a dilation when asked to constrict, and there is a little bit of constriction when asked to dilate. So in other words, again, this is statistically insignificant. There is no evidence whatsoever that participants can voluntarily do this. We haven't discovered anything new. We have just confirmed what is already known in the field with our own participants to rule out this possibility. But Galton had a little bit of a different questions. We have a situation in which we are relying much on information on working memory. But in his questionnaire, Galton is asking questions based on long-term memory. Things like, what did you have breakfast this morning? Now, between now and breakfast, there are lots of things that have happened. So you haven't possibly kept in mind, or during all this time, what you had for breakfast. The question, of course, came up unexpectedly. In our experiment with triangles, instead, we had a situation in which participants knew what they were supposed to do, and therefore would very likely hold in working memory the representation of that image, and then they continue to hold it in mind, in fact, generate a mental image when asked to do so. So we decided then to recruit other subjects, and this time imagine familiar situations, just like Galton did in this questionnaire. And in all cases, doing the same type of experiment, participants looked at the same gray empty screen that we used previously. So we had all imaginary scenarios. So imagine that you're looking at the sunny sky, at the night sky, or a cloud sky, or that you are in a completely dark room. We also, to come a bit closer to Galton's example, specific objects, how do they look like? So So we decided to use an object that everyone should be capable of creating a method in a job. Think of the face of your mother. But think of the face of your mother in two different situations. One in which the face of your mother is in full sunlight, and one in which the face of your mother is in the shadow. Okay? To test the difference between these two. And of course we don't know what people are actually thinking at any time, because we haven't shown anything to stimulate. But we know that in a lifetime of experiences with these kinds of things, there should be a clear difference in luminance for each one of these scenarios, so that we can make specific predictions. Some should have more brightness in the image if mental imagery preserves the sensible feature of perception, and more in some situations and less in other situations. So, in fact, one of the questions is exactly the question that, one of the questions that was asked by Galton. Imagine that you are looking directly into the sun. It's a sunny day, you're looking directly into the sun. And one of the respondents, so Galton wrote down all the responses, is this: I feel as though I was dazzled when recalling the sun to my mental vision. Okay? This is introspection. The question is, would this person also show at the same time a constriction of the pupil? Because that would be physiological evidence which cannot be faked, that when we think about these objects, something happens in our visual cortex that repeats to some extent the experience that we have when we look at an actual sunny sky, and that in turn triggers a series of physiological adjustment and adaptation as if we were actually in that situation. And that includes the pupil size responses and possibly other bodily adjustments that consist with the experience. So again, we don't know what people are imagining, but a cloudy sky, a night sky will have on average different type of experiences, and dark room and so on, so that indeed we find that each of them, sunny sky, night sky, cloudy sky, facing sunlight, facing shade, the dark room, produces different responses in the pupil. These are confidence intervals. So many of these comparisons are significantly different from one another. In fact, what causes the largest constriction is thinking about the sunny sky. Remember, everyone is in a laboratory looking at the gray screen at all times, okay? And this is significantly constrict. Indeed, thinking about a night sky or a cloudy sky, sorry if I'm covering your vision, it creates dilations, as you would expect, okay? And thinking about an object, the face of your mother in sunlight, constricts again the pupil. And in fact, it does that significantly differently than thinking about the same object when it's in the shadow, which reverses the effect to a dilation. And what causes the largest dilation is to imagine that you are in your room, you have locked everything, doors, turned off all the lights, you have the curtains on the window, there is no light coming in, it's a perfectly dark room, and then this provokes a remarkable dilation of the pupil. So, bottom line is that, yes, the eye pupil adjusts also to imaginary light, not just illusory light, also light that is simply not there, that does not exist at all. So to wrap up this, I think all of these results are related to one another, because when it comes to the illusions, the brightness illusion or illusions of glare are objects that, far from being special, far from being unusual or artificial, they simulate things that are found in nature and events in nature that can have consequences on our survival, as a matter of fact. Glare is a huge problem nowadays in modern society. Each year, thousands of people die in car accidents that are caused by glare effects. This is nowadays, but we can also think that being blinded by light momentarily can have great consequences also in our past evolutionary time, when we were looking for prey, or perhaps during combat with another person. So that situation would also cost our life. So there are utilities attached to this response to an illusion. If you are capable of responding to a clue, a hint, that this is probably going to happen, then you would have saved your life or spared a lot of problems and so on. The same argument, I think, applies to imagery. Imagery, a function, one of the main functions of imagery, is also to prepare ourselves to what is about to come, to whatever next. So if we imagine, for example, a directional motion of an object, something, we will be able to perceive it faster and better, even when the stimulus is degraded, even when the information wouldn't be sufficient to suggest the presence of the stimulus when it is actually there. So imagery is probably a mechanism that has evolved also to help our brain to predict the future as part of predictive cognition and so on. So this is my personal account. Thank you very much for your attention.